materials informatics related talks, and this is one of them, but probably a little bit more into the core of our machine learning engines, which are behind a lot of materials informatics. Specifically, I will talk about approaches to machine learning, which I call them networks and kernel methods to capitalize on the advantages of both and hopefully minimize the disadvantages of both. I will start by probably the most fastest introduction into kernel regression as well as neural network, because I will need that information to then assemble the hybrid approaches. Many of you have seen pictures like this of a neural network as being a collection of so-called neural activation functions. I will show a multi-layer version of it later, which would be approximating a multivariate function f from some feature vector x by forming linear combinations of the components of x, feeding them into neural activation functions, and then collecting the outputs into either the outputs or into the next layer of neural activation functions, and that's a neural network. And oftentimes when you read introductory text on neural networks, you will see an analogy with biological neural networks. You will see pictures maybe like this from multi-layer neural networks. I don't necessarily find the analogy with biological neural networks very helpful. I look at these objects as expansions of a non-direct product basis. So if you look at this very simple equation, which in fact is the equation for a single hidden layer neural network, where I can imagine that the output neuron, which would have been here, split to the left-hand side, which I can always imagine. This is a basis expansion. This is expansion with linear coefficient C over a basis of sigma of neuron activation functions. And these sigmas could be different for different neurons, but typically they are not. The reason they are not has to do with nonlinear optimization. I will mention a few words about that later. What is interesting here is that this is a non-direct product basis. The parameters W and B parameterize the basis function sigma n, and it forms a non-direct flexible product basis. And this is important. Neural activation function sigma could be any smooth nonlinear functions. Often they could be things like sigmoids or ReLU types of functions, etc. But they could be any smooth nonlinear functions. And it's important to remember that a single hidden layer NN is a universal approximator, and you need to think carefully if you actually need a deep or multi-layer neural network, because those come at the cost of a very large number of nonlinear parameters, and very many nonlinear parameters means dangers of overfitting cost. So this is a nasty thing. The multi-layer NN could then be expressed in the same kind of ideology as this kind of Russian doll type nested expansion, where you can still view the outer hidden layers, the outer nonlinear layer of neurons as a non-direct, as a definition of a non-direct product basis. It pays to play with the neural activation function of a neural network. For example, using simple exponential neurons, you immediately arrive at a sum of product expansion of your function, which is very important if you want to integrate a function. You don't want to integrate a 100-dimensional function, but it's very easy to integrate a product of one-dimensional functions. Other approaches for sum of products have also been proposed. All references in color will be to our work. All blacks are in to others' literature. I mentioned that a single hidden layer and then is a universal approximator. What it means is that for this expansion I wrote on the page before, there is for any as smallest as desired accuracy of the approximation delta, there is a finite number of neurons which achieves this accuracy. That's the essence of the universal approximation theorems, and those theorems are data ignorant. This says nothing about the data set you have or you may need to achieve your delta anywhere in space. And this is an important aspect because it's the data density, the sampling density, which ultimately limits the accuracy of the neural network model. So the thing which I would like you to remember from this slide is a huge number of nonlinear parameters may be required, especially in multi-layer neural networks. We will now to kernel methods. Kernel methods also can be viewed as expansion of a non-direct product basis. The kernel methods, whether Gaussian process regression or the kernel-rich regression or support vector machine, have exactly the same map of the representation of the target function f of x. So the language about Gaussian processes, etc., I find it not particularly useful. It has to do a lot with how one optimal or decides on hyperparameters. The form of the approximation is exactly the same, and it's a linear regression in a nonlinear basis, where the basis functions are built from the kernel functions. The kernel functions are often taken as type of meta family of functions for the GPR version of kernel regression. This looks like a rather messy thing with the gamma functions, etc., and Bessel functions. But for specific hyperparameters new here, this defaults to your conventional radial basis function or squared exponential type kernels or simple exponential type kernels. So these kernels still have hyperparameters which defines, for example, the width of this basis function, L. This L can also be used to read some insight from otherwise general method, which GPR or KR is. And that's the basis of the so-called automated relevance determination, whereby if you have some automated way to find L, to optimize it to some criterion, for example, maximum likelihood estimation, then small L would imply larger influence of a particular variable and long L otherwise. And I will return to this issue of getting some insight from an otherwise generic kernel method a little bit later. The fact that it's a type of linear regression is very, very important. The basis is nonlinear, but the regression is linear. And because of that, it is a robust thing. So this is a thing that combines the robustness of a linear regression with the high expressive power of nonlinear methods. However, to solve for the coefficients, you would need to invert this matrix called covariance matrix, which is made from calling the kernel functions that you're using for all pairs of points in your data set, and that becomes expensive for large data sets. Moreover, the defining equations of these kernel regressions actually do not depend on the dimensionality D of the data set, and that's a great thing. That's contrary to neural networks, where right off the bat you can see that the number of terms here would scale with the dimensionality of the data. This is not the case for kernel regressions. However, when the dimensionality becomes very, very high, this approximation basically dies when you use meta family of functions. I gave examples of 1,000-dimensional data sets where the approximation dies in a seminar here and in RS 2 years ago, so I will not repeat that example. I will show you some other examples. So as I mentioned, the important thing for machine learning is that it's a non-direct product type of representation, and because of that, it allows one to palliate this so-called the dimensionality scaling problem, or the curse of dimensionality, which means that when the dimensionality palliate the sparsity of sampling by throwing more data as the problems, the density of sampling will always remain small, and you have to use methods which are available to work with small sampling density. Machine learning methods avoiding direct product representations, think, for example, Fourier type representations, which are direct product representations. They help with this, and that's why they are great in high-dimensional spaces. But when the dimensionality becomes sufficiently high, they will also die, and you need something beyond the off-the-shelf methods, and that's what we are trying to do, something which would work with extremely sparse data, and something which would work under these other interesting conditions which you might observe in high-dimensional spaces, for example, loss of the property of locality. Let's speak a little bit about loss of the property of locality. So we had talks here about potential interatomic potentials, and I will give here an example from the fitting of interatomic potentials. We work on small molecules because we work on computational spectroscopy, accurate computational spectroscopy. So these are not solid-state interatomic potentials. These are just molecular interatomic potentials. So 3-dimensional case for water molecule, 6-dimensional case for formaldehyde, and a 15-dimensional case for uranium hexafluoride. In all cases, we use several thousand training data. We sample this potential energy surface in the spectroscopically relevant region around the potential minimum with several thousand data. And lo and behold, when we look at the distribution, the histogram of the values of this covariance matrix K over our training set, what we observe is that for the low-dimensional cases, these values are all over the place, which means that there are many of these Gaussian RBF type kernels which go close to zero. As you increase the dimensionality of these values, the minimum values in this distribution become higher and higher. For the uranium hexafluoride, there is no locality. So the property of locality of the magnum type kernel has been lost because of sufficiently high dimensionality of the space and low dimensionality of the data, low density of the data. Why is that happening? That is happening because for highly dimensional cases, this optimal X parameter, optimal means giving you the best quality of approximation in all space. We monitor that by using very large test sets. Forget 80-20, we use huge test sets. We use, for example, 10 times in our evaluations of methods, we use 10 times more test data than we use the training data. And there are applications where the data is not the problem. You just don't want to use all of them for training because the matrix to invert is very, very large. So, so if by monitoring the quality of the model in all space, we can identify the optimal hyperparameter L, and it turns out that it tends to become so large in high-dimensional settings that you lose the property of locality of the kernel. As you lose the property of locality of the kernel, you also lose the advantage of multi-zeta type ideas. The multi-zeta bases, which people in the electronic structure will use all the time, they are intrinsically located to the property of locality of the basis function. And if the property of locality is effectively lost due to the high dimensionality, any advantage of double zeta or triple zeta would be lost. And we see it as well by comparing, for example, the test set errors in the potential energy surface as we increase the number of training points between the 3D case, 6D case, and the 15D case, where for low dimensional cases, there is a significant advantage of the double Z approach, which is here in the orange bars versus a single Z kernel, while for the high dimensional cases, there is a full loss of any advantage of the double Z idea over just a single Z idea because the optimal hyperparameter is simply too long, right? And we can see it also when we compute highly accurate vibrational spectra. This table is specifically for H2CO, where we monitor the quality of the lowest 100 vibrational levels, and we can indeed observe the improvement in the error in these levels and the error in the ZPE when we go from the single zeta kernel for the expression of the potential energy surface to the double zeta kernel. In the case of the formaldehyde, we still see the advantage in the RMSE of the potential, and this advantage transfers into the advantage is the quality of the vibrational spectrum, right? So high D, the property of the locality is lost. What else happens in high D? Again, looking at the H2CO potential energy surface, trained on about 5,000 training points, we're using a lot of test points. We understand that even when we scale the coordinates, the six interatomic distances are part of the 6 coordinates and angles, right? So there's 3 distances and 3 angles, which form the coordinate, the space of coordinates of this molecule. We scale them either in max scaling or normalization. Even in the 6D case, the optimal hyperparameter is larger than the range of the coordinates. But we still have the property of locality here. We get extremely highly accurate machine learning. So this is the correlation plot, right? Model versus the truth. So these are extremely diagonal. We can get very highly accurate model. What we can do now is that say, okay, in a high dimensional case, my length parameter will be very, very large. I can artificially make it large. The quality of the fit will, of course, drop. And then what I notice is that it drops and it becomes equivalent to a low order polynomial or regression. We can simulate already in the ideology of the kernel regression, we can simulate a low order polynomial regression by using the so-called dot product kernel showed here. In this case, it's a third order dot product kernel. One can show very easily that once you use a dot product kernel, it effectively a polynomial regression. And we observe that when the length parameter is very, very large, we essentially get a low order polynomial regression. Well, in high dimensional cases, the length parameter becomes very, very large. We just identify that. That's why you lose the property of locality. And in this situation, there is no advantage of using highly expressive RBF kernels versus just using a simple polynomial regression, which one can obtain either from dot product kernels or directly fitting a polynomial model. We can see also, we can simulate this kind of artificially causing the data density to be as low as it is in the uranium hexafluoride case by using very few training points. For example, only 150 training points. That gives us a density of sampling comparative to what we get in 15D with thousands of training points. And we see exactly the same thing. The quality of the model drops and is fully reproducible without any RBF kernels, any of these so-called highly expressive kernels with a simple polynomial model. So your model essentially collapses, your kernel regression then just collapses to a simple polynomial approximation because your dimensionality is so high and the data density is so low that you simply cannot have sufficiently short length parameters in the kernel. So this is important. So what to do then? So this is all ultimately it has to do with the fact that in this kernel regression, one uses the kernel, which is a full dimensional kernel, that the X in the kernel, the dimensionality of the X in the kernel is the dimensionality of the X on which the function depends. Well, if the problem is due to the high-dimensional kernels, well, don't do high-dimensional kernels. It's very simple. Let's build a multivariate function with kernels of low dimensionality. Enter the expansion over orders of coupling. Some people call it high-dimensional modular representation. So the HDML language comes from the Rabbits group at Princeton, who formalized this kind of modelization about 20 plus years ago. But of course, people in physics know this as the multi-body expansion. People in chemical physics or spectroscopy would often talk about the N-mode approximation. People in the statistical world, of course, know very well the analysis of variance, the ANOVA decomposition, which has been used for about 100 years. All of these are expansions over orders of coupling. It turns out that in most situations which are important for life, you don't have to use in this expansion the small d, which is the maximum order you retain in the expansion, equal to the capital D. For most situations important in real life, the small d at which you cut this expansion can be as small as 2, 3, 4. Very rarely do you need to go beyond 3 or beyond 4. Only in highly accurate spectroscopy do you need to go up to 4. And in most cases, 2 or 3 would be good enough. We can also lump, in this expansion, we can lump any lower dimensional terms into a small d dimensional terms, which is a dimensionality we have to use from the accuracy perspective. And then it's basically a representation of a capital D dimensional function as a sum of a bunch of small d dimensional functions. And that's good. Why? Because the low dimensional terms here are easier to build. For example, if you build them with machine learning, your machine learning method will work in its comfort zone. You will not have these horrible super high dimensional kernels which lose the locality property. And they're easy to use. Remember, for example, the case of multidimensional integration. You don't want to integrate a 100-dimensional function. It's easy to integrate a 3-dimensional function. So over the years, we developed a machine learning-based method based on the expansion over the orders of coupling, where these terms, which we retain, the small d-dimensional terms, are represented either as neural networks or as Gaussian process regressions, a kernel-rich regression, whatever you want to call them. Specifically, in the case of kernel regression, it's very easy to show that it suffices to select the kernel of the approximation in the form of a sum of low-dimensional terms, and then you can very easily drill through the equation to show that the final functional approximation will also be as a fallout as a sum of these low-dimensional terms. So you can use your preferred kernel method in Python or MATLAB. You just define a kernel in this additive form. It's called additive GPI. It has been already the Rasmussen book on Gaussian process regressions mentions it, and the DVNO paper deals with it, but those applications that typically deal with rather low accuracy settings, nothing like examples I've been showing here, which are super high accuracy. And I will show you an even higher accuracy, required accuracy example later on, unless I run out of time, which is also very much possible, right? So additive kernels, the kernels which are sums of sub-dimensional function, and okay, great, are very powerful. You build functions which are made of lower dimensional functions. The Kolmogorov theorem, the neural network world knows this, is basically it starts by saying we'll represent the multivariate function as a sum of one-dimensional functions. Here we say we'll represent the multivariate function as a sum of sub-dimensional functions. So these worlds are related. Another huge advantage of this kind of expansion is when your density of data is sparse, and the density of data is always low in sufficiently high dimensional settings, you will not be able to recover the full dimensional function. So already 20 years ago, also in the realm of molecular potential energy surfaces, we showed that the density of sampling ultimately limits the order of terms, the dimensionality of terms that is recoverable. For each density of sampling, there is a maximum small d, where the term is actually recoverable. If you have a high-dimensional, 100-dimensional data sets, you have 10,000 sampling data, you will never recover a 100-dimensional function. So why would you even try? If you know that the terms that are recoverable are 4-dimensional, well, begin by building a set of 4-dimensional functions. And your approximation will then be more robust. Another way this is useful is that you can use this kind of models as surrogate models. Why? Because when the density is very low, you can recover maybe 1-dimensional, maybe 2-dimensional terms, but let's say maybe not 3-dimensional terms. Well, recover what you can recover, let's say 1-dimensional terms, and then use the 1-dimensional expansion it's a simple additive model, which is a sum of one-dimensional terms, to simply generate more data computationally. And we have shown it recently in the case, again, fitting the potential energy surveys of uranium hexafluoride, where because of the sparsity of the data, if we were, for example, to do GPR on the data and try to use something like maximum likelihood estimator, which is the often used method to find the hyperparameters of the kernel, it would result in rubbish. The data are simply not enough for the method to even latch on and do proper hyperparameter optimization. But if we use this data to recover first only the simple additive model, a sum of one-dimensional functions, it's a rather crappy approximation, not a very good fit, a decent fit, but not a very good fit. But I can then use this fit to generate more and more and more and more data. And it turns out if I then run an automatic, for example, MLE-based hyperparameter estimation on the generated data, the optimal hyperparameter which comes out of that, so those data, we'll call them reference data, the 1D reference data, they are not exactly the same as would have been optimal for the full 15-dimensional data set, but close enough, good enough. So these expansions can be used as surrogate models to help, as crutches to help, for example, find optimal hyperparameters. So this is also important. Now let me connect the walls of GPR, and specifically of this kind of additive GPR, which we achieve by using an additive kernel, and the world of neural networks. Let me stare at this expression for a single hidden layer neural network. What I'm looking at here is essentially an additive model in new coordinates, which are the arguments of neural activation functions. So these are some coordinates in which this model is a sum of one-dimensional terms. I will come to this on the next slide in more detail. In a traditional NN, you would fit parameters W and B, and you would fix the shape of sigma, and the sigma would be one and the same for all neurons. It is convenient to use one and the same sigma for all neurons because you would use backpropagation to facilitate training of the NN, and that's hugely facilitated by using one and the same shape of sigma. But I don't want to train a zillion nonlinear parameters W and B, so I will not. If you look at the old literature on neural networks, when this field was growing in 1980s, 1990s, people often talk about rich NNs. Why rich NNs? Because imagine this is a sigmoid, and this is the equation of a plane. So this essentially defines planes through space, which are then optimized as you optimize the parameters, and the sigmoid kind of creates the rich, hence the rich NN. So instead of letting W and B be optimized and taking the cost of nonlinear optimization and the dangers of overfitting, I will define W and B. I will define how to pass these planes through space, for example, with some random or pseudo-random algorithm. And to recover whatever I lost by not fitting them, I will instead find the optimal shape of sigma, which is optimal for each W and B. Outright, it doesn't sound like a good proposition. Why is it easier to find the shape of the function when I could simply do fitting of the parameters, which I know how to do? But it is simple. It turns out it is simpler. Why is it simpler? Because, as I said, when we stare at this equation long enough, we understand this is an additive model in some new coordinates y. So this would be y1, y2, y3, etc. I have n, a redundant number of new coordinates y, which are the linear combinations of my original coordinates x. And in y, this is an additive model. But I have just shown on the example of additive kernels that I can build additive models very, very easily. I can simply fit this, this problem with an additive GPR in y. And if I do that, so if I decide on the shape of these W's and B's by passing these planes through space myself with some rules, and the rule we use is using a Sobel sequence to make sure we don't do it randomly, but pseudo-random. Because randomness, when the data density is low, is not quite random. So to really be random, we use a pseudo-random sequence. So once I have defined these y's, I define an additive kernel in y, and in one linear step, all of the shapes of fi fall out. So all the shapes of this neural activation functions, which are optimal for my data, optimal for my W and B, come out in one linear step. There is no nonlinear optimization done anywhere. And because I don't do any nonlinear optimization, I am robust. But because the equation I'm building in X is a neural network, in Y is a GPR, So it carries all the properties of single hidden layer neural network in universal approximation, the power of representation. So its expressive power is as high as of any neural network, but it's as robust as linear regression. And I can see that on the example of fitting anything, for example, a potential energy surface of, for example, water molecule, which I'm fitting by throwing in more and more of these terms, which are essentially more and more neurons, right? In X and more terms in additive GPR in Y. In a normal neural network, you would level off to some minimum test error, which would be limited by the density of sampling. You put in more neurons than necessary, so your error will go up. In my case, I can put as many N as I want here. So the error will level off. The minimum error is limited by the density of sampling. And then it just stays there. I'm as robust as linear regression. There is no nonlinear optimization done anywhere. I don't have any overfitting. I don't need to know the exact architecture of the NF. I know I need at least of maybe 50 neurons. I can throw in a 50 or 100 or 200. We don't care. It doesn't cause any overheating. Is it cheap or expensive to throwing in an extra 100 neurons? It's absolutely cheap. The only extra cost is summation of the kernel. The governing equations are the governing equations of GPR. They don't depend on the number of neurons. It's only the extra summation when I define the kernel that matters. So this is something that, if you look at the shapes, by the way, of these functions which are built by GPR, they can be anything. So these are some examples of the shapes. And the magnitudes of these terms can also serve to understand the importance of either the original variables X or their combinations which are formed when we form Y. And now I'm going, in the remaining few minutes, I will go for a materials informatics example to show you how this works. That should be still fine. 5 minutes for my questions, right? And then questions in 5. Yeah.
Questions in
So it's 11, 5th, so I've been speaking for 18 minutes. Not too bad. Okay. So this is how it plays out in an example of materials informatics that we all love. So we're going to machine learn deformation energies and band gaps, which we just seen a typical example of that just before. And we will be looking at the mixed perovskites. Without further ado, let me just say that this kind of mixed perovskite structures are important for optoelectronic technologies, including solar cells, and people would like to design perovskites which are unstable and present desired band gap. So the structure type is shown here. It has A type, B1 plus, B3 plus side, and the X, which is the halogen side. For the A side, it's either potassium, rubidium, or cesiums that we are playing with. For the B sides, it's a bunch of metals, and X are the halogens, chlorine, or bromine, or iodine. The data that we use are straight from this article in NPG Computational Materials. So we simply borrow, they were nice enough to actually provide this data set. And in their paper, they use trees, and we're going to play with our new method and show that it's better. So this, what is used here to learn the band gaps and the formation energy are about 30 descriptors, which consist of atomic parameters like electronegativity, radii of different SPDF orbitals, ionization potentials, and distances between cations and the nearest halogen atom. So this forms a descriptor of chemical composition and structure, and from that set of descriptors, I'll be learning the band gaps and the formation energies. I'll be using my new method and we'll compare it to something else. So the very first thing I have done is I will say I'm going to use this funny method which I just introduced, except I'm not going to bother introducing any Y's. I'll just do it directly in X. If I do it directly in X, it defaults to additive GPR in X in the original coordinates and can therefore be used by monitoring the magnitudes of terms that additive GPR built to decide on the importance of variance. Well, that's a way alternative to the ARP, which I introduced when introducing GPR. So if we do that, we see that the quality of the additive model, for example, learning the band gap, is not high. It means you want coupling. The coupling isn't the problem. But it still shows a trend, and it's good enough for me to look at the importance of variables, to look at the importance of these different terms, and to understand that some of these terms are actually not important, so I can throw them out and end up working with 20 plus instead of 30 plus variables. So that's one utility of this additive kernels, right? So now I'm going to proceed throwing in the coupling terms, just as I described in the slides here, where I can throw any number until convergence, and that's not expensive because no nonlinear optimization is done. So this is how it works. I'm throwing any number of neurons at this problem, and I'm monitoring the root mean square error in the band gap. So this is a correlation plot. This is how the error behaves on the test and train set when I simply increase the number of neurons. I'm not plotting I'm not showing here the example for the information energy, because information energy turns out is much easier to learn. So this is very diagonal. But for the band gap, we obtain 0.2 eV or even lower on the test set. If we look at what has been done before, in particular in this paper, where a gradient boost decision tree was used, then in the visible region where they learn a GGA band gap, the error can be as high as 1 eV and therefore is not actionable. Our errors are 0.2 eV in the entire range, including the visible region, and it's not just different, it's not just a different method, it's better. Okay, so this is this is a method which goes off the shelf and hybridizes neural networks and kernel with kernel-rich regression with additive kernel. I will skip one more example here, which I wanted to show you, but in the interest of time, I will skip it. And summarize, as Jonathan telling me I should, right? That machine learning is, of course, very useful in high-dimensional settings. And the reason it is useful is because machine learning techniques avoid the so-called direct product representation. But eventually, once the data density will be low enough, and it will always be low enough when the dimensionality is high enough, even those methods will fail, and you need something of the shell. Many nonlinear parameters in neural networks is one of the problems. They cause cost, they cause overfitting, they cause scaling with dimensionality. The kernels don't scale, the defining equations don't scale with dimensionality, but in practice it might be difficult due to the density of sampling. And you cannot palliate this issue by throwing more data as a problem due to the curse of dimensionality. The kernel methods are attractive because they're effectively linear regressions and therefore as robust as linear regressions and gain the expressive power through the kernel. But the kernel might lose its expressive power in high D due to the low density of sampling. So the way we palliate this, we use additive kernels. We use kernels which are sums of subdimensional terms which do not have that problem and retain expressive power and gain in robustness. In particular, we can hybridize the ideas of neural network and kernel methods by recognizing that a single hidden layer neural network, a universal approximator, has exactly the same form as an additive model in a redundant set of coordinates. We define those coordinates with rules without any nonlinear optimization. And then additive kernel GPR, additive kernel KNR, builds us all these terms in one go. And those terms, their shapes are optimal. We can think of them as optimal shapes of neural activation functions of the neural network. We obtain a method which is as robust as a neural network, as linear regression, as expressive as a neural network. And one way this appears is that we don't see any overfitting as we add more and more neurons into the problem. So all of this essentially shows that there's value in going beyond off-the-shelf method, especially for very high-dimensional, low data density settings. The examples I showed had to do with materials informatics and molecular physics, essentially, but the methods are very, very general. We also play with learning functionals for orbital free DFT with this kind of approaches, but I didn't have time to talk about that. So with that, thank you for your attention. I'll try to answer any questions.
Thank you very much for a fascinating talk. Do we have time for one very quick question? I think.
Why do we still have 5 minutes?
I think we start from 20 past.
Yeah, we are 5 minutes late.
Okay, sorry.
Yeah.
I didn't realize
No
that.
worries. Yes.
I think you mentioned the high dimensional we cannot need more than 4 order function.
Yeah.
Yeah. Does that affect the count of years? And then to use larger count here to have to use more?
No, it's different. So you're thinking in terms of the cutoff radius business. When we do, for example, when we have small molecule potential energy surface, the entire cutoff radius business does not even kick in at all. So this is something which is way more general than the limits due to the cutoff radius. Moreover, it is a small, when you think in terms of, for example, cutoff radii, like when you do MD, for example, etc., it is at the small distance that you have most coupling. When you go long range, the coupling defaults to basically two-body models. So this analogy, I don't think it works.
Do you have any suggestion?
Do
you have any suggestion how to reach the cutoff radius?
There is no cut. I don't know. I don't work with cutoff radii. The cutoff radius means that you neglect terms which are beyond certain radius. It's the higher order, the higher coupling terms are more important in the short distance, not in the long distance. So you are taking this the other way around.
I think in the interest of time, we should stop here. I think there's probably more questions to be asked in the lunch break.
Let's have discussion times. That's why. Yeah.
Thank you.
Thank
Thank you very much.
you.